Thank you. Okay, so this is the first part of the tutorial. So acknowledgments, disclaimers, and the most important things. So this is based on collaborative works that I've done with my students at UT and USC. Facebook collaborators, especially the systems part that motivates the technologically relevant questions that we've been recently looking at. So also Vivek and Zach, who have been collaborators, and also I call them every now and then. And I say, hey, is this still open? Has there been a recent paper that I'm missing, and all that? My advisors, of course, who I worked on these problems, and Nihar and Rashmi, who are here at Berkeley, who work on this, and the organizers for inviting me, of course. Now, disclaimer is I will try to focus a lot on open problems and what is not known in this area. And the problem is that this is actively evolving. So if I miss something that is not open, and I think it is, please let me know. Okay. Now, there's two parts in this tutorial. The first one I will focus on regenerating codes. And this is what I will do today. And the second part, I will focus on other things that we have been doing, including locality that Parikshit gave a very nice tutorial before. But I will basically go over a few things a little differently, and then some extensions of locality that we call availability, and recent work actually with collaboration with Anna, who's here, on batch codes. So this is the second part for tomorrow. Okay, so this is my motivation sort of slide. This is an actual trace from a Facebook cluster that has 3,000 machines. So this is a Hadoop cluster that stores analytics data. So it's not a front-facing cluster that you interact with as a customer, but rather in the back end. And the important thing to notice here is those were 3,000 machines, and this is a trace of how many machines were failing at any given time. Now, failing, you have to define exactly what you mean by failing. It's not that it exploded necessarily. That it could be that the machine was just unavailable for 20 minutes or a few hours, which is still a problem if you try to read the data that is in that machine. So this is like the issue of currently available versus actual failure of data. Now, the thing to look here is that you could have as many as 100 machines failing in a day, in a bad day. Okay. Now, a machine in this specific cluster was storing typically around 15 terabytes, 10 to 15 terabytes of data. Those were pretty big machines. So if you have a machine that has crashed, and you have to recreate the information that was lost in that machine, and the main point that kind of is we should be motivated about is that if you have 20 nodes that are down in a given day, and that's a pretty good day if you see this, because 22 is here, so most days you have more than 22, then you have approximately 300 terabytes of lost data that you need to repair. And if you use Reed-Solomon coding, as I will explain in a second, for every bit that you lose, if you repair, you have to, in this specific Reed-Solomon that they're using here, you have to do 10x. So for every bit you lose, you have to communicate 10 times that to repair that one bit. I will explain what repair means in a second, but I'm just giving you the motivation. So there's a ridiculous amount of communication that needs to happen in the cluster to repair the data that is lost. I will define what I mean, but I'm just motivating it here. So we estimate that 30% maybe of the network traffic in this cluster is yes?
Alex, but you said that it's for a couple of hours. Why would you repair things if it's for...
Okay, so if it is very good. So most, it depends. Not all of it is for a couple of hours. Some of it is for... So the real world is complicated. Now, if it's being decommissioned, as they say, then they need to repair it. Even if it is that's one case where they need to repair. Another case where they need to repair is if it is unavailable, but someone still wants to read the data.
No, that, of course,
so that's the degraded read, which is...
But that's probability of this happening. It's like 300 terabytes compared to the size of the cluster.
Right. So the question is how often queries will try to read this data. And in fact, as far as I understand, and Parikshit can tell us more, but the main reason that people motivate this is in current clusters in analytics is the degraded read. So it is things that you try to read data that is currently not, the server that stores the systematic block is not available right now, and you still want to read it, you issue a repair job that is not to reconstruct for fault tolerance, but rather for performance of a query. Yeah. So, but in reality, that's a real bottleneck. Okay, so that's why Reed-Solomon codes are not suitable, and that's why Microsoft and others are switching to using modern distributed storage codes. So, okay, now let's go in theory land and explain exactly what we mean. Okay, now storing stuff with linear equations. So when I say, I will draw pictures like this, right? And I say, some node, I will call them storage nodes like machines, some node stores A, some node stores B, some node stores a parity, etc. Now when I say that a node stores A, let's just go back here. Let's say you know nothing about coding theory. In fact, throughout the talk, you don't need to know coding theory. You need to know linear algebra, okay? So I'll just do everything linear algebra way. Okay, linear algebra is, when I say somebody stores A, it just stores something that says A is 3, okay? And we can think of arithmetic modulo a prime, if you want, or just normal arithmetic is fine too, except very few parts of the talk. So when you store A is 3 in one machine, and you store B is 1 in another machine, and then in another you store A plus B is 4, so you store the linear equation and the output of the linear equation, right? So this is, for example, a very simple code, a 4,2 code. And it contains two systematic symbols, that is A and B, these two numbers here. And these 4 linear equations that you're storing in these two numbers. And the generator matrix of the code is this K by N matrix. And it has this nice property, as you can see, that if you lose any 2 out of these 4 storage nodes, you can reconstruct the data, right? So for example, and I just realized I can do this in PowerPoint, observe. I can do this. I can go here, and I say, now you lose this, and you lose this. Let's say this one. Okay. So now, and when you actually lose them, what you really lose is really this stuff, right? So you don't know this one. You know that you had a node that was storing A and B, but you don't know the 4 and the 3. And of course, this will be very big, right? This will be in the megabytes, so don't think of it as actually a small number. Okay, so now you've lost 2 things. If we go, can you reconstruct? Of course you can, because you have 2 linear equations that have rank 2. If we look at it in the generator matrix, so this here is the generator matrix, so you lost this column, and you lost this column. And the reason you can reconstruct is because this matrix has all its square submatrices that are full rank, right? So that's great. So an MDS code, as it's called, is a K by N matrix that has the nice property that all its square submatrices are full rank, okay? And now, if you don't know anything about coding theory, you say, okay, how hard can that be, right? If I just randomly choose numbers, I'll get a matrix where all the square submatrices will be full rank, but it's not that easy in a finite field, right? So Reed-Solomon codes is an explicit way of constructing matrices that have the property that all the square submatrices are full rank in a small field. Is that the smallest field where you can do it? Nobody knows. So there's a famous MDS conjecture that the smallest field where you can create this matrix where all the square submatrices are full rank is the Reed-Solomon construction. And I guess Venka told me there has been some recent progress on this, but it's still open in general. It's all for prime fields. Okay, very good. Okay, so everything here is classic, very good. Now, the only thing I want to say here is that instead of thinking that I store A is 3, think that A is actually going to be 64 megabytes. That's how big it is in Hadoop, for example. And then you repeat the same code, many times, right? So you store across, and now when you say A plus B, you XOR these and you repeat the same code, thousands of times. So these are very big, but the overhead of storing what is the equation is small. So we always think of the numbers as big. Okay. Now, what is repair? Repair is the following very basic problem. I was actually really surprised. I was talking with here in Nefeli actually with a CS grad student, Sean Rea, who told me that this is a problem they have in a peer-to-peer system where they use read Solomon and they lose one equation. That's the most common thing. The most common thing is one failure. So repair means you have a single erasure, so you don't know B, and you want to reconstruct it. Okay, that's not a problem. We said you can tolerate any two erasures, right? So you can definitely tolerate one. The issue is, okay, here you want to recreate what you lost, B. How much communication do you need to do in a network to recreate what you lost? This is the repair bandwidth problem, right? The repair communication problem. How many bits need to be communicated to reconstruct one lost symbol? Is that clear? Because if it's not, this will be a very boring talk. Okay, very good. Both are interesting, but let's think about any symbol for now. Okay, so how much communication do I need to repair a single lost symbol? For example, this really basic question, I'm embarrassed to say that for its Solomon codes, we don't know the answer. Okay, so let's first think about a few trivial things. So the first trivial thing is, obviously, if you send any two symbols, you can recreate the lost symbol, right? Okay, for example, this guy, which we call the newcomer, can communicate to these two guys, say, hey, what is A plus B? This guy will say A plus B is 4. This guy will say A plus 2B is 5. So you send two symbols from here, you send nothing. This guy now has two linear equations in two unknowns. He can solve for B, throw away A, happy times, okay? Very easy. Can you do it with less? So that was the main thing we realized, is that you can actually reconstruct one symbol by communicating less than two symbols. That's the punchline. Is that surprising now? I don't know. Back then it was. So my claim is that I can actually repair a single symbol with 1.5 symbols by communicating 1.5 symbols, and I will also prove to you that this is optimal. But not for its Solomon. You have to give me the power to design my own crazy MDS code to do that. Okay, what the hell does it mean to communicate 1.5 symbol? Communicating 1.5 symbol is the idea of what we call subpacketization, which means splitting your symbols into half symbols. And for example, we'll be doing linear equations over half symbols and forming what we sometimes call vector linear operations. So is the problem clear to everyone? Please let me know if it's not. Okay. So I'm just going to do it for this 4,2 MDS code. Okay. So here is the construction that I'll use. So instead of before we had 4 nodes, right? And every node was storing one linear equation. Now I'm going to have one node, this one, and this one node will be storing 2 linear equations. And I have split my symbols into half symbols, okay? So I have now 4 half symbols, x1, x2, x3, x4, and this node is storing 2 of them, and this node is storing 2 of them, and this guy is storing 2 linear equations, 2 half linear equations, and this guy is storing 2 half linear equations. Now, is it true that this is an MDS code, a 4,2 MDS code? Well, I have to show you that if you lose any 2 nodes, for example, maybe you lose this node and you lose this node, you can still reconstruct all the data, and it's true here because you are going to get 4 linear equations in 4 unknowns, okay? So that's fine. So this is a 4,2 MDS code that has been subpacketized. The subpacketization level here is 2. Okay, now I lose the first node and I need to recreate it here. The trivial thing to do would be to send, for example, these 2 packets and these 2 packets, totally sending 2 symbols, right? And I claim I can do it with 1.5 symbols, which means I can do it by communicating 3 of those packets. Okay. Can I do that? Another trick that I will be doing here that we don't know when I need to do it exactly, but I will do it in this case, is if I want, these 2 things are collocated, so I can create a linear combination of them if I want to locally and send that, right? And I will be doing that. So I can mix the local stuff here, mix it here, and then the things I send is what I'm paying for in this problem. Okay. So let's just try something simple. So I can choose, for example, coefficients 1 and 1, basically effectively XORing these two packets and create a packet x3 and x4 and give it to this guy. Okay. Now let's understand one thing. This guy wants to solve for x1 and x2. Okay. He doesn't want x3 or x4. So x3 and x4 is junk to this guy. It's irrelevant information, interference. So that's why I make it red. So this equation seems to be completely useless to this guy because it involves things he's not interested in, but it will be actually very useful, as we will see in a second. Okay, so I can choose any coefficients I like to create any local linear combination I like that is then going to be transferred in the network, and I need to transfer 3 packets total to match my promise to you. Okay, so I choose 1 and 1 and I do this. So let's see this. Is this going to work? What do you think? If you're nodding, don't. No, this doesn't work. So why doesn't this work? What's the problem? What's happening here? What do all these symbols mean?
Get rid of the exports.
Right, so let's look at, now this thing is created locally at this node, and this is communicated over the network, right? Okay, so I am communicating, as I promised to you, 3 half symbols. That's cool. Now, what are these 3 half symbols? These are 3 linear equations, okay? This equation says x3 plus x4 is 53. This one says this is, 50,000 or something, and this something like that. Now, this guy gets these 3 linear equations. These are 3 linear equations in 4 unknowns, and he wants to solve for 2 of them. Unfortunately, if I give you 3 linear equations in 4 unknowns, you cannot solve for 2 of them, right? Okay. In fact, these 3 linear equations cannot be solved for x1, x2. And now maybe you can see the trick that I'm going to do. I'm going to massage these linear equations in a way that they are solvable for x1 and x2. So how can I do that?
There's got to be many ways.
There are many ways. So the power I have is choosing these coefficients, right? Okay. So what I need to do is I need to make sure that the undesirable stuff is cancelable, right? Okay, so this is the idea of interference alignment, exactly. So interference is this subspace that is undesired, and I need to make sure that it appears with the same coefficients in these 2 equations. So if I could make these coefficients, for example, 1, 1, and 1, 1, then I could use this linear equation to cancel out the undesired stuff in the other 2, and this guy would be very happy. He would be able to solve for the things he wants. And the way that we did it, so we realized this in 2009 with Yunan Wu, that if we choose this coefficient to be the inverse of this and this coefficient to be the inverse of this, we have aligned the interference to this one, and then here we can set it to be whatever we wanted, so that you can use this linear equation to cancel out these 2 and recover the desired symbol. Okay? So this is interference alignment, 3 equations in 4 variables that are solvable for 2 of the unknowns. Okay? So now I was able to repair a 4,2 code by communicating, a 4,2 MDS code, because this is an MDS code, by communicating 1.5 symbols, as I promised to you. And there are a few questions now that are obvious. The first one is, okay, what about a 5.2 code or a 5.3 code or any other code? What's the minimum repair communication? And for this question, we did not know if you can do this trick. Already, the moment you add another symbol here, systematic symbol, you will not have enough power in your coefficients to align. So there's a baby version of interference alignment here where you say, okay, how many linear alignments do I need? This many. How many coefficients do I have to choose stuff from? This many. Okay, do I have enough degrees of freedom to make it work? And that only works for very few cases, and these are the cases that we discovered. But there are other papers in interference alignment, starting from Kandam Ben Jafar and Kandani's work, that were showing that you could align way more stuff if you were careful about designing your original code in the right way. And we did not know how to use that technique in general, but then other people who did were able to solve this problem in general. So right now, there are ways for any n, k code to design that code in a way that you match the optimal repair communication. I will talk about that in a second. These are called MSR codes, and it doesn't stand for Microsoft Research. It stands for minimum storage regenerating codes. The problem is that they are not practical. They require, so you see what I did here is I split a packet into two things that I call sub-packets. In general, we need to split into a ridiculous number that I think in the first works was doubly exponential. Right now, the state of the art is exponential. And we basically don't know if we can do it in a polynomial sub-packetization. The field size we need is also exponential. So basically, we have codes that are MDS and are optimally repairable, but we don't have practical MDS regenerating codes to the best of my understanding right now. So I will talk about that a little bit more.
About the lower bound?
So the lower bound is through the information flow graph, the cutset bound. Is that what? Oh, for the field size. So there is work on lower bounding the field size, and there's work on lower bounding sub-packetization. So if you limit yourself, so I'll talk about it. Yeah, but very good. Yeah, there are some lower bounds, but they're not valid in general. They have some limitations, to the best of my understanding. Okay. So we understand the problem, right? Okay. So cool. So let me tell you a little bit about how we can prove the lower bound in communication. So maybe you could do less than 1.5 symbols, right? Maybe you could do 0.5 symbols. That's clearly not possible, because at the end of the day you will create one symbol, so you better communicate one symbol. But maybe one symbol is achievable. Okay. So we saw that in a 4,2 code 1.5 symbols suffices. I will show that this is also necessary, and I will use a flow argument. Okay, what's the flow argument? So this is the thing I lost. This is the newcomer. And this newcomer is going to connect to the existing storage nodes and download beta bits from each of the existing storage nodes. Observe that I'm choosing here the symmetric point where you download beta from each. If you understand this proof, you will be able to very quickly prove yourself that the symmetric point is actually the best point. All right, so let's understand how to give a lower bound on beta. Okay. So first I add a virtual super source where all the information in the universe originates. Okay. I connect this super source with links of capacity infinity to those. Now I'm doing this trick where I split every storage node in two parts, and I put this green arrow, which is how much information is stored in this storage node. So this is the storage node today, this is the storage node tomorrow, and this represents storage, this link here. And then I said, well, this newcomer communicated with the three surviving nodes and downloaded beta bits from each. That's fine. The capacity here is 1, so I say 1 megabyte, I mean 1 symbol. Just think of it that way. Okay? And now I'm putting this guy that I call a data collector. What's a data collector? A data collector corresponds to, remember, what are we trying to do? We need these three symbols and the new symbol to form a 4,2 MDS code. That means that any two out of these four must give me all my data. Somebody's calling me. It's not a good time. So any two must give me all the data, right? So let's choose this specific set of two. This specific set of two must have enough information to reconstruct all the data. So I claim that there must be enough flow from the source of all the information to this guy. How much flow do I need? I need all the data, which in this case is 2 symbols, right? So if I find a cut separating the source to this data collector that is smaller than 2 symbols, it's clearly impossible that I have repaired this node. So this is the argument. Is this clear? Okay. So now I'm going to find a cut that separates the source to this data collector, and I'm going to cut this edge. The capacity of this edge is 1 symbol, and I'm going to cut these two. And first of all, you see that this is a cut. There's no way to travel from the source to this data collector without going through these 3 edges. And now the capacity of this is 1. The capacity of this is beta, and beta, I'm trying to give a bound on those. So the value of the cut is 1 plus 2 beta. And 1 plus 2 beta has to be bigger than the total amount of information, which is 2. Therefore, you get that beta has to be greater than 1/2. Okay. I'll just say the same thing. Yes?
I guess I'm missing something.
Yeah.
Why do the betas all have to be the same?
Very good. So they don't have to be the same, but if they are different, beta 1, beta 2, beta 3, I can choose a set of 2 nodes. Remember, any 2 out of the 4 must give me the data back, right? So you choose any betas you want. I will choose the 2 smallest ones and put them in the cut. And I will get that any 2 must be greater or equal to 2, and I will get that the sum of them is minimized in the symmetric case. Is that clear? So yeah, you can prove that the symmetric is the minimizing the sum of the repair communication. Okay, another way of saying this, going back here, is, okay, let's just go back here. I'll just say the same thing in a different way. Remember, we're trying to create here something so that any 2 out of these 4 recreate the data, right? The data is 2 megabytes, okay. Now, let's take these 2. These 2 must know everything about the data, but this guy got everything he learned from here, you're already getting from here. So this is useless, and this is 1 megabyte you're getting from here. So this information better be 1 megabyte also, right? That's exactly the same thing as what I said before. I'm just telling you the same argument in another way. Okay, so that's how you can prove that the repair communication must be greater than 1/2. Now, another thing that is important here is that we can make a little relaxation to the repair problem. We can say, instead of recreating exactly the linear equation that was lost, I can take a step back and say, okay, you know what? Don't recreate exactly the linear equation you lost. Create a new linear equation that just has the property that is in general position compared to the others, which means that you just created a new MDS code now. So you change the code, but it's still MDS, which means that any 2 out of these new 4 equations are full rank. Now, if you could do that, that is called functional repair. And it's an easier problem than exact repair. And the question is, what is the minimum amount of communication to do functional repair? So in the first paper that we did, which was basically the main paper in my dissertation, we were able to completely characterize the repair communication for functional repair. And the reason is understanding this graph that looks complicated, that says that functional repair is really multicasting and nothing more. Okay, now what does that mean? So an MDS code, so I'll just write something here. So a 4,2 MDS code is this, okay, so this is a source, and these are 4 symbols. And the 4,2 MDS code means that any 2 out of these 4 symbols allow you to reconstruct your data, right? So we can view this as a multicasting problem where I put a data collector for these 2 and the data collector for these 2. And you get the idea, right? So for any 2, so I'm going to put for choose 2 data collectors, which correspond to all possible failure patterns. And an MDS code is simply a way to create linear equations that travel through this graph that satisfy all these 4 choose 2 ways of reconstructing the data, right? Okay, so that is a multicasting problem. And now there's two arguments that we're using here. The first one is that if there is a single data collector, a single sink that doesn't have enough flow to the source, then you're definitely screwed. There's definitely no way to do it. But if you want simultaneously to satisfy all these guys with the same linear equations, are you guaranteed that there is a code if each one individually has sufficient flow? That is true, but highly non-trivial, right? So that is basically the network coding multicasting theorem that generalizes max flow min cut, that says that if you're sending the same information to multiple receivers, if the minimum of the min cuts is satisfied, there is a way to satisfy all of them simultaneously. And furthermore, it's very easy. All you need is general position. So you just randomly choose linear equations in a big field, and by Schwarzschild, you're happy. Okay. So functional repair is exactly equivalent to multicasting on this graph that I call the information flow graph. And let's see how. Okay, good. So The issue that we need to worry about here, so now this graph is exactly this graph that I was drawing here, but in addition I had a failure, so now I'm making the newcomer who connects and downloads beta bits from each, and I added all the 4 choose 2 data collectors connecting to the 3 surviving storage nodes and the newcomer. Okay? And as long as the minimum cut separating this source to all of them is sufficient, then I know that there is a code, and furthermore, just random linear combinations will suffice. And the problem is, of course, this code will be changing. These linear equations here will not be the same as these linear equations here. They will be changing. So that's why it's functional repair. Okay? Furthermore, you can think of a more general problem where, okay, maybe this node failed and I repaired it, but maybe this node failed and now I repair it somewhere, and maybe this node failed and I repaired it. So you can think of all sorts of stuff that can happen, right? So in order to be guaranteed that you have enough flow, you need to create all possible failure patterns to infinity, connect them, and find the minimum cut in this infinite graph. So that's what we basically did. So I'll show you that in a second. Okay, so the first statement is that if you care about functional repair, it is possible to functionally repair an MDS code by communicating this many bits, as opposed to the naive scheme, which was communicating the data object, which was k symbols. Okay, so here the size of a symbol is b over k. B is the total size of the file you are storing. So in this paper, we were able to characterize the functional repair communication. And I mean, this is an example. If each of your blocks is 64 megabytes, which is what is done in Hadoop, and you just have a 4,6 code, the naive repair communication will be 256 megabytes, whereas if you have optimal repair communication, it will be 160. So even for very small cases, you can get substantial benefit. And asymptotically, it's even more interesting because it scales completely differently, right? It scales like in the order of 1 symbol as opposed to the order of k symbols. So there is a very big gap between naive and optimal. Okay. Furthermore, the other thing we realized back then is that if you increase the storage per node a little bit, so you give me a few extra bits in each node, so you make your symbols a little fatter, but you still want to recover from any k symbols, so now you're no longer an MDS code, then you're going to get much better in repair communication. So there was a trade-off between repair communication and storage. And the way that this is computed is through this infinite graph that I mentioned a little bit before. So here is the graph. You have the source of everything in the universe. These are your original n storage nodes. Every storage node stores alpha bits. Before, if your file was b, alpha was b over k, right? So you were storing. That's an MDS code. Okay, but now I'm going to allow you to be a little bit over that if you want. And now you have some failure, any failure, I don't know, and you introduce a new storage node that has degree d. This is how many of the existing nodes he connects to, and downloads beta bits from each of them. And you could be analyzing the non-symmetric case too, but let's worry about the symmetric for now. So this guy is going to connect somewhere here, and then maybe there's another failure, so you have a new repair, and maybe this connects to the newcomer and some other people, and another failure. So these all possible things that can happen will form an infinite graph here. And now what do you want from this infinite graph? What you want is that any k things in this process, so you choose any k nodes you want, like this one, this one, this one, and you put a data collector, and these links have capacity infinity, and you need to make sure that the flow, or the min cut from this source to this data collector is bigger than the file you're storing. And you need this for all infinitely many data collectors. Okay? So the game we're playing here is that in this infinite graph that can be formed in any way possible, I need a way to get bound on this number, and this number, so that the flow is sufficiently high. It exceeds the file. Yes?
Do you have to indicate which ones you lost when you create the new one?
No, I'm going to do it for any set of failures. So it sounds complicated, but it actually isn't, because you can find the worst case failure sequence that will characterize the cut, and you can prove that any other failure sequence will give you a bigger.
Okay, so before when you showed, for example, that first node there, it was connected just to the guys who weren't failed, but now you're going to connect it to all, right?
No, he could connect. In general, I'm going to do this for any degree D, any repair communication beta, and any alpha, and I'm going to create all possible failure patterns. So I could allow this to connect to any D. So D is the parameter that you're asking, I guess. D, in my previous example, was 3. Yeah, but I can compute this for any D. Yeah.
This is actually slightly stronger because let's say you had one node failure.
Yeah.
You don't really care to require it's a new node and the
I don't.
node are linearly independent, right?
Exactly. I could just decide that I had this n, k code and I wanted to go to an n+1 k code instead. So there's not really an issue of failure here. It's creating a new symbol. It's creating a new linear equation that's in general position compared to existing linear equations. So maybe you had your code and you decided I need a new redundant symbol, but I don't have all the data in one place. I need to create this new linear equation by connecting to some other linear equations. So you could do that. Yes?
Alex, and in the original network coding paper, wasn't the field size somehow a function of the size of a graph?
Yes. Yeah, so now, okay, very good. So now I'm in trouble. So in the first paper, we said, okay, we're only going to analyze a finite case, and we get a field size that's exponential in the graph, indeed. And then there is a follow-up paper where we actually show that even for the infinite graph, we can do it with a finite field that doesn't scale.
Then of course you use the structure of the graph.
Well, you use the fact that even though there's infinitely many data collectors, there's finite types of, yes. Observe, by the way, that if I was doing exact repair, none of this business would be a problem, because the moment I have recreated this, I'm back to my previous problem, right? So if I had exact repair, I don't have to worry about this, but I have to worry about much harder stuff, right? So, okay, so it turns out that you can calculate the min cut of this infinite graph, and from this min cut, you're going to get the minimum, the best choices of parameters, alpha, beta, and D. You're basically finding a cut in this graph. And so this is the main theorem that we had proven, that for any n, k code, each node stores alpha bits, repairs from D existing nodes, and downloads D times beta, right? This is the total amount of information communicated. We call that gamma. The feasible region is a piecewise linear function that's complicated. I don't expect you to parse it, but it's just piecewise linear, and it looks like this. So this is the storage per node, alpha. This is the bandwidth or repair communication, beta times D. And the minimum storage point, the MDS point, is when the storage per node is the minimal possible. Remember, from any k nodes I need to reconstruct, right? So the minimum storage per node is beta over k. So this is a horizontal line. It doesn't get any better now. So MDS codes live on this line, and the question I was asking before is, what am I doing here? Yeah, storage is here. So the question is, how much can you push in this direction? How small can you make repair communication, right?
Just to understand, the scale on the y-axis is in units of the original source size, is that right?
The scale is, okay, so...
One is the total source, because it seems like you've got k equals 5, so 0.2
yeah.
corresponds to 1/5.
Right. So this is 1/5, exactly. Yeah, very good.
You meant B over K.
Yes, I'm sorry, you're right. I meant B over K, because the Greek uppercase B is also called beta. Very good, yeah. Okay, so yes, so this is 1/5, and this is a k equals 5 code. So this is the MDS, and the question of what is the minimum storage point is how small can you make repair communication while staying MDS. And for example, for the 4,2 case, we said that it's 1.5. In general, we have a formula for it, but we need to construct the code in a very painful way to match it. Okay, good. So now this is the region for functional repair, and everything outside this region for functional repair is impossible because I show the cutset bound, right? So it's information theoretically impossible. So this is also called the cutset region. Yes, please, yes.
You also have d equals n minus 1 here. How does it change as you reduce d?
Very good. So the other question we asked is, well, maybe if you talk to more people, you're getting fewer stuff from each, but it wasn't clear how the tension between repair communication behaves. If you look at this, you can prove that D is n-1 is the case that minimizes repair communication. So the best thing to do if you want to minimize repair communication is talk to everyone who survived and download a little bit from each. That's provable by the cutset. Everything I'm saying is for functional repair. And the real question that we wanted to solve is exact repair, right? So furthermore, now I need to enforce that the lost equation is equal to the new equation that was lost. And of course, the exact repair region is something inside this, but we don't know where it is. So this was a question we have been working on for the past, 5-6 years now. So I'll tell you the story. Okay, so initially we discovered this 4,2 example that I showed you that was surprising to me, that said that, oh, even for 4,2 MDS code, you can do better than the naive thing with exact repair. And then Rashmi Sain Kumar, I guess, the first paper is here, where they showed that for this point, which is called minimum bandwidth regenerating code, MBR, which allows me to store a little bit more per node, you can match the cutset. So they created a code for this case. That's very beautiful combinatorial construction. This is 2011, and then there was a sequence of papers in 2000 up to 2012 by all these people, including my group and the Berkeley group, the Pierre Kumar's group, and UT Austin Sriram's group, that were able to construct codes for the minimum storage point. Initially, we had good codes for rates up to 1/2, and then there was a paper that used interference alignment that was able to show it for all codes, but with the subpacketization being exponential. And still, we don't know how to achieve this point with polynomial subpacketization. Okay, so then you see now this red thing is starting to approach the blue thing, and you're saying, okay, I can conjecture that the whole cutset region is achievable for exact repair, and I did conjecture that. I was actually offering 12 bottles of ouzo in proving or disproving that the exact repair region matches the cutset bound. And Chao Tian, who was then at AT&T, actually disproved it. And he disproved with a very interesting proof that takes the Shannon inequalities, the polytope defined by the mutual information greater or equal to 0 inequalities, which are exponentially many, of course, in a computer-assisted proof, and he was able to demonstrate an inequality that slices through the cutset region. And in fact, for a very small code, he was able to fully characterize the exact repair region by finding also a code inside here, and saying that, oh, for the 4.3 case, a very small code, we know the full exact repair region, and it's different from the functional. And for that reason, this is a photo of Chao with 12 bottles of wine. So he didn't want ouzo. He said, I hate ouzo, as probably most people, and I sent him some Greek wine instead. So okay, but you see, and now I will just mention some open problems we have a little bit of time, and so the first open problem, the biggest one, is what is the exact repair region, right? So this has been open for a while now. We know that it's not the cutset region. The original proof in Chao Tian's paper, I don't really parse it very well. I mean, it's basically, okay, the polytope is like, 50 inequalities from the polytope, massages them in some very interesting ways too, because even for that case, without massaging them, I think it was intractable. So he had to find some symmetries to make a tractable thing that he would feed in a computer program. So also I think it's the first computer-assisted proof in information theory that is not to prove an inequality, but rather for an engineering problem. So still it's open, and it's very interesting. I guess we don't even know if we need non-Shannon type inequalities to characterize the exact repair region. So that's probably the biggest open problem in the area of regenerating codes.
So he didn't use non-Shannon inequality?
Oh, okay, so again, to the best of my understanding, it's only Shannon inequalities in his proof.
Oh, I see.
So and for that he says that for the 4-3 code, Shannon inequalities alone are sufficient to characterize the exact repair region, and the exact repair region is not what you get just by computing the cuts, because the way I got the blue thing is I computed all the cuts in this infinite graph. Right? So but that's not the case in his. Yes.
Is there any correspondence of the red region to some entropic region, or?
Yeah. So of course, I mean any problem in information theory you can characterize it as a. So if you want, you can write. I mean, I think there's papers like that. Probably most recent by Babak Hasibi, right? You say you write down what you want from your reconstruction, so you can write it in terms of entropies, right? Basically, you say I need. So you can do this, right? So what you do is you go here, and you say I need the entropy of the data given the things that this guy observes to be 0. That means he can reconstruct. So basically, functional repair will have reconstruction conditions only on these data collectors. Okay? And then you just have the fundamental inequalities of just Shannon for now. Now, if you want exact repair, you have to also enforce that these intermediate guys reconstruct the same linear equation that was stored in the thing they were repairing. That's what makes it much harder. So basically the statement I'm making in terms of Shannon in the Shannon polytope is that adding these extra conditions, the partial reconstruction conditions, changes the polytope. Yeah.
So that only makes sense to me if d is n-1, because then you know which one you're repairing. But if d is smaller than n-1, how do you know which one you're repairing?
You would have to choose which one. Yeah, so then it would be, you would have to work over all possibilities. Okay. Yeah, which would be even messier. Actually, this looks very difficult, and it is not. Because the cutset, so maybe I'll show this since I have time. There is a simple graph that is the worst graph that characterizes the worst cut. And after you realize that, you just have to find the cut on that worst graph. What is the worst graph? So I'll show it to you. It's actually very easy and very intuitive. So the worst graph is the following thing. It's what you would expect. So you have a source, and you have your n storage nodes. Okay. Now you have a failure. Okay. Now you repair. Now you can repair from any d you want. So if we set d is n-1, we don't have to worry about that. So let's just do it for now. It doesn't matter, but okay, actually I don't even need it. So let's just say that you connect to some d, okay, and you repair from those. Now you have another failure. So maybe you could have this failing or this failing or this failing. What's the worst thing in terms of flow? The worst thing in terms of flow is you kill the oldest people. Okay? So you always kill the oldest people. So so you kill this person, now you repair this guy. He also has a choice, right? He could be repaired from old people or from young people. And as you know, young people are less wise than old people. So the worst situation is when he connects to the newcomer and these folks. And now you have another failure. What's the worst failure? Again, the wisest, right? So you want to kill an old person again, and you have a newcomer, and the newcomer again should connect to the least wise people. And this, and this. So this is the graph this is the sequence. You can prove that this sequence produces the worst cut. And actually the proof of that is not hard, and then also finding the cut in this graph is not hard. So that's where this region is obtained. Okay. So and it's very intuitive, right? Because the older people get more flow, so to speak. Okay. So good. So that's the first open problem. Is this clear?
Well, can you demonstrate the code with the storage less than 1/k? Just for fun. I mean, is there a simple example?
No, it's impossible because my
Less than greater than 1/k. Yeah.
Oh yeah. So first of all, just to say this, the reason it is impossible is I need any k to reconstruct, right? So yeah, unless you are in non-symmetric.
I meant for the other point.
Okay, for the minimum bandwidth generating point. Yeah. So.
Anything in between, But as long as it's simple, as your original 422 example.
There is one really nice construction by Rashmi and Nihar. It's basically what you do is you build an expander graph or any graph that has like large neighborhoods, and you make the packets, if I remember correctly, to be the edges, and so the packets are the edges. Sorry, am I saying this correctly? Okay, can you remind me is it a complete graph that you do? No, what was the graph?
You can do a complete graph, or there are more general constructions as well.
Right. So Salim, I guess, had some later. Right. Yeah. So there are some very nice purely combinatorial constructions where the things you store are edges in a graph, and the nodes of storage are the vertices in the graph, and then you can prove that they match exactly the MBR bound. I don't have a slide on it, but there are some really beautiful constructions actually. So for this point. Okay, now the one problem I guess is we don't have a lot of constructions for the intermediate region, and we don't even know the intermediate region. Okay, so that's the first problem. Second problem, because I need to wrap up. Open problem number 2. For the MSR point, for the minimum storage point, which means MDS codes, all known exact minimum storage constructions require exponential field size and exponential subpacketization. In fact, there are 3 constructions that were concurrently done in 2012. One of them by my group, the Hadamard code, as we were calling it, Hadamard designs, I guess. Kadambe and Tamo had concurrent, and all these 3 constructions we think are basically almost equivalent. But the Tamo construction has a benefit if there's only 2 parities, then he has a small field. But in general, we don't have any way of doing polynomial field size and polynomial subpacketization for MSR codes. Furthermore, okay, so there are some practical constructions that are not optimal. One of them is the piggyback paper that appeared in SIGCOMM this year. The other important thing about this paper is that they actually implemented it in Hadoop, which is a very hard thing to do. I can guarantee you that. So that was a practical construction that is the closest, I guess, we have to an implementable minimum storage engineering code. And the main open problem I think here is, can we approach or even possibly match the minimum storage point with polynomial subpacketization so that it's actually a code that people in Facebook, can use. So that's an important open problem here. Are there any questions on this? Okay. And another open problem that I think is embarrassing a little bit is, what's the best repair communication for a Reed-Solomon code, right? So that's like a classic object. How much information do you need to communicate to reconstruct? Obviously, you can reconstruct a symbol by communicating case symbols, right? Can you do it with less? Yes. So we have a paper in 2012 that if you mess around, but you remember, to do it with less, you have to hack the field, right? You have to send half field things. So you have to define what the hell that means. So you open the field and you look at the field and there's a few ways you can do that. So you need to create a linear algebra, so to speak, in the subfields, and we do that. I guess people who work with extension fields could think about it in different ways too. But we have just one construction that improves over the trivial thing of sending case symbols. Observation: in order to have any hope of benefit, you need to connect to more than k nodes, right? So if you connect to any k, you communicate case symbols and you repair. Now, in order to, in the regenerating codes, if you want to get a benefit, you have to connect to more than k and get smaller things from each. And now the same question can hold for any family of codes, like Reed-Muller, even node, etc. How do you repair these codes? Even a non-trivial scheme for repairing Reed-Muller, for example, I think is open. For even node, there is one construction. So that's another important open problem. Now, the last thing is for tomorrow's lecture, I'll just say everything I said so far was on the number of bits that are communicated in the network during a single failure. That's called repair bandwidth. There are these 2 other metrics that practitioners tell me that are important. One of them is the number of bits that you read from the disks during repair, which can be different. And the other one is the number of nodes that you access to repair. That's called locality. That's the previous tutorial. So for this problem, basically, we don't know the capacity. I had a conjecture on the capacity that was disproved. As I said, we only know some points. For this problem, I don't think we know a lot of things that are non-trivial, so it's quite a wide open problem. And for this problem, we know the capacity for most cases. I guess that Tammenberg is the state of the art for this, for codes also that have small finite field, which I think are working for most parameters, as long as there's a polynomial, a constant polynomial that can be constructed. There's a technical issue there. So in the next lecture, I will talk about this problem and some extensions of that, and I will stop here.
Any other questions?
I think a very important question is, what are you offering 12 bottles of ozone for next?
Yeah, good question. Let me think about it, and maybe tomorrow I can do something. Yeah.
You might want an upgraded price as well. Right?
Yeah. That's a good question.
So this MDS conjecture that was put in the prime case actually says that not just that it gives a characterization of the optimal codes. It says that optimal codes are in some sense equivalent to Reed-Solomon. Do you have some such conjectures for this type of codes? That optimal codes have just one solution, unique solution?
No, I think we know much less about this problem than for the MDS. The related question in this problem is what's the minimum field where you can perform exact repair. Even if you do functional repair, which is basically multicasting, it's open, right? The minimum field for, I don't know, Amina maybe knows this better. What's if I give you a multicasting problem, the smallest field size that you can create a multicasting code is open, right?
Yes, in general it's open. So for if you have only two sources, then we know, and have a tight bound and everything. That's sort of 10 years. And in one direction, we kind of derived it immediately. It took us another year to find. But when you have n, it's not. We still kind of believe that it's square root of n, as in two cases, but we are not sure. And then it becomes like the arc problem in the alphabet size, except that now in this Reed-Solomon, you may have some zeros to respect. Maybe I'll tell you more.
But actually, I'm thinking about it now. I can even tell you a much more embarrassing situation. I don't even know if I need exponential field size. So
that's my question. Yeah.
Yeah. So I don't even. No. Just so I don't know how to construct. I don't know a single code for this point, exact repair, that needs polynomial field size. Yeah.
So,
Am I making
yeah.
Okay.
Something interesting there is if you are okay with rate greater than half, rate less.
Oh yes, sure.
If you're okay with rate less than half, then you can do it in quadratic field size. But as soon as you cross the half barrier, the known constructions, they blow up.
Yeah, very good. Yeah. So there's a distinction here. If for rates below half, there are very many practical constructions. I guess the product matrix and the eigenvector construction are the two that are very neat and practical. But for high rate codes, greater than half, which I think is the case where many people in storage care about a lot, we don't have anything. So yes, very good. Yeah.
So one way to maybe characterize this mathematically, so you have these matrices, and you have, like you said, you're forcing some zeros there, and you have some requirements, some determinants are non-zero, and you're asking, well, a random assignment is sort of, you take into account the unit bound of all possible things, and this is a bed, but you can do something smart.
Exactly. That's the same way you prove, like if you try to create an MDS code which is random, you'll just get an exponential field size. So can we do better? And for MDS you can, Reed-Solomon. For this problem, I don't know. Yeah, but there was a question exactly aligned to you. Why? Yes.
Not behind me, right?
No, yeah.
So your result on beating K for Reed-Solomon, how much do you beat it by?
Very little. Asymptotically, very little. So if we have a decent benefit when n minus k is constant. So for a constant number of parities, we get something. But
square root k, or is it k by 2?
Oh, I don't know how it asymptotically how it vanishes, but it definitely, if your code has constant rate and NK grow, it vanishes. The benefit vanishes. I haven't figured out how, but yeah, definitely does.
Also, Alex, so practically speaking, I mean, so I had a sort of argument with Sergey yesterday because he also believes that field size is important. To me, I don't understand. I mean, your codes practically, I mean, Facebook is not going to use n equals million ever, right? It's always going to be like a few hundred maybe. So why not you? I mean, you can implement in hardware very cheaply 2 to the 64 field.
Yeah. So okay. So there's fair enough. So I'll tell you. Yeah. So first of all, n. So there's many things, right? So there's block length, there's subpacketization, field size. Okay. Now, field size I can make if I store bytes, like the current Hadoop thing, RAID, HDFS RAID uses bytes. So you're working with 2 to the 8. You can convince them to go to 2 to the 16, 2 to the 32. I don't think you can convince them to go above that because it will be a pain to implement and performance-wise and all that. So I think that's the field. But the much bigger problem than the field size itself is the subpacketization, because the subpacketization you have to have logic that deals with the subpackets, and if they are 1,000, which is not a big number, then you will have a lot of pain. So I think subpacketization is a bigger problem than field size itself.
Coefficients will also come from the big field, like this was something which I think came up in Pariksha.
Yeah, the coefficients will can come from I think 2 to the 6.
Size.
But the subpacket size is you can make them big if you want to by growing them in this direction, right? So okay, so just to clarify something here. So how do I do this? Oh, there we are. Yeah. So if you have big blocks, you can, even with binary, you can make them big by repeating the same code. So that's fine. Now you need a little bit of power in your field, so you group the bits in pairs of 2 or pairs of 8, and you work. That's how you make the field bigger. So your blocks can be 64 megabytes, but your field size, one symbol, is not 64 megabytes, right? So you can always repeat the code, and that's how you go to bigger things. The things they don't like is NNK being bigger than 20 or 30 or 40, because for many reasons, overheads keeping track of blocks. And also they don't like subpackets, I think, being a lot, because they have to keep track of subpackets in metadata, and I think the metadata storage explodes because they're storing billions of files. So yeah. So I think subpacketization, to the best of my understanding, practically subpacketization is a biggest issue than field size. But field size, ridiculous field size above 2 to the 32, I think would also make it impractical.
It bothers me, something in geometry that we don't understand somehow. That's why it would be nice to solve.
Yeah, I mean, fundamentally, yeah. So there's many worlds, right? So, but for both, I think this is very interesting questions. Yeah.
Good that you had time left at the end, because you got a lot of good questions and good discussion. That's always a good thing. Thank you very much again. It was a great talk.
Thank you.